Good afternoon, everybody. Good evening, good morning, wherever you are in the world. Welcome to my broadcast. My name is Diana Hooper, and I'm a theoretical physicist currently doing a postdoc over at the ULB in Belgium. My speciality is cosmology, which means I study the universe, the contents of the universe, how everything evolves, basically everything happening inside the universe. Hey, David, thanks for stopping by. Great to see you here. So I know I'm on a different day than usual. I'm usually broadcasting Sundays, my time, 5:30 in the afternoon, Central European Summertime. Today is not Sunday, today is indeed Monday. Hi David, other David in here. Thank you for joining, and thank you for the hi award to anybody watching. Make sure you follow the two Davids here in the comments, both very much worth following here on Happs. So I usually broadcast on Sundays. This weekend I was actually away. Hey Sally, nice to see you, and thank you for the appreciate award. I really much appreciate it. Hey Desiree, nice to see you too. Welcome, thank you for joining. Thank you everybody for being here. So I'm usually live on Sundays. This weekend I was actually not planning on doing a broadcast. I've been away the last couple of days, much needed break. Today is actually a holiday in Germany, where I currently am, and in Belgium, where I'm technically working. So I wasn't planning on doing a broadcast, but then the Happs people announced on Friday that the theme for this week is space. And how can I not do a broadcast when the theme is space? So I have to be here for the space week. So this is my participation into the Happs Space Challenge. Do check out everybody else who's done a broadcast for Happs Space Challenge. Amazing broadcasters here on Happs. I'm sure there's a lot of amazing space broadcasts already. Hey Ange, nice to see you. You are not late. Actually, I started 10 minutes late. Sorry about that. I was, as I said, I was out, came back today, got back a bit later than planned, and then had to rush a bit with the setup. So that's why I'm 10 minutes late. Apologies, everybody, for the delay. You didn't know that was the theme. Well, David, you still have a few days, and I know you're going to do a broadcast about the eclipse, if you haven't already. So definitely follow David here for his space broadcast as well. Hey, Pablo, thank you for joining. Nice to see you here. Doing my Happs Space Challenge, because I cannot miss the Space Week. So I have to do my Happs Space Challenge. So, as always, I'm going to just ramble about things that I like about the universe today, with a specific focus on fun space facts, which is a very broad topic. You're all welcome to jump in at any point with questions, with comments, with anything that's not clear, anything you want me to repeat. Feel free to jump in and, just jump in, ask me questions at any point. You already did 2 broadcasts about the total lunar eclipse. Well, they should definitely, did I say solar eclipse? I meant lunar eclipse. The total lunar eclipse broadcast should definitely count towards a space. Well, maybe just go back, edit the title, add Happs Space Challenge to the title, and there you go. Okay, so we're going to talk about some fun space facts. There's a lot of fun space facts. So today's theme is basically just reminding us all that we're kind of small and insignificant, and the universe is ridiculously big. And we're going to review a few things that will hopefully leave you with the idea that the universe is huge, we're kind of tiny, but the universe is amazing, and it's great that we're here to study the universe. Now, my broadcast usually lasts 1 hour. We have a lot of stuff I want to cover today, so I think 1 hour is rather ambitious of me. So, the first thing we're going to discuss is the fact that space is a lot bigger than you think it is. The universe is a lot bigger than we can possibly imagine. And we don't really need to see all of the universe to get an idea of this. So we're going to start just by focusing on the solar system, our local neighborhood. We have our star, we have the sun, we have 8 planets. Sorry, Pluto. Pluto is not a planet. We have 8 main planets. We have a few dwarf planets, a few small rocks floating around, about 200 moons by now that we know of. A lot of stuff in the solar system. But the solar system is also mostly empty space, like most of the universe, but the solar system is pretty much completely empty space. So in order to see this, I'm going to bring up my screen share. I'm going to use a lot of the Happs features today, the screen share, bringing up images, and at some point I have notifiers as well. Seeing as Happs gives me these amazing tools, we might as well use them. So this is a really cool web page that we're going to go through, and I know you can't see the page itself, so I am going to post it here in the comments as well, so that you can all go to this page if you want to at some point. This is a great page. So the page that we're looking at here is a visualization, a to-scale visualization of what the solar system would look like if the moon is scaled down to 1 pixel on our screen. So the moon is going to occupy 1 pixel. All of the other planets, moons, and even the sun are going to be scaled according to this pixel width. So this means that 1 pixel is the size of the moon, which we'll see in a minute exactly how many kilometers that is. Hey Do, nice to see you. Thank you for being here. It's so great to have you here on the broadcast. That's a cool title, right? If the moon were only 1 pixel. So this is the idea. The moon has been scaled down to 1 pixel, and what we're going to see is the size of the planets, the moons, the sun, and more importantly, the distance in between them, scaled to this idea that the moon occupies 1 pixel. Put the link here in the comments as well in case you want to check out this page as well. So if the moon were only 1 pixel, a tediously accurate scale model of the solar system. And we're just going to scroll. Now, here it explains the scale, just so we're all clear here. 1 pixel is what the size of the moon is, which is going to be about 3,500 kilometers. I am going to be working in kilometers. Apologies to anybody who uses the non-metric system, but we will be mostly working in kilometers. At some point, I'll actually change units and show you some other cool units. So we have this nice ruler, so anything that occupies kind of this space across here is going to be 1 million kilometers. Okay, this is an incredibly cool site. I know, David, this site's amazing. So we're going to get started. Now remember, our comparison is that the moon is 1 pixel, so here you can see the size of the sun, which is considerably more than 1 pixel. But now comes the fun thing. Now we want to scroll gradually to find the other planets. And always down here at the bottom of your screen, the bottom of my screen even, you should be able to see this distance that we've gone from the sun. So if we start right at the beginning, we're at 0 kilometers from the sun. And now we're going to start our journey and see where we find our first planet. Now I've scrolled a bit. We've already traveled 10 million kilometers. That's quite a lot. Just scrolled 10 million kilometers. Let's carry on scrolling and see where we find our first planet. As you can see, this page has a lot of fun comments that will be popping up time to time. Wait, I just remembered. I didn't give you the fun fact about the sun. Let's go back. I have a lot of fun space facts that I'm supposed to randomly tell you. And my first one is actually about the sun. So I need my sun back. Okay, so you might have heard me say, you might have heard a lot of people say before that the light from the sun takes about 8.5 minutes to reach us. And this is true. Any light emitted from the sun will travel at the speed of light, and it will take it 8.5 minutes to reach us here on Earth. But these photons, these particles of light that we receive from the sun, are actually produced thousands or even millions of years ago. So if you imagine that at the center of the sun, you produce a photon, a particle of light. In order for this particle to reach us, it first has to escape the inside of the sun. Now, a lot of people make the comment, and I just made it as well, that it takes thousands or millions of years for this photon to escape the sun. And this is actually not completely true, because it will not be the same photon. So what happens in the sun is there's a series of absorption and emission processes. So you create a photon at the center of the sun. It will travel a small distance, and then it will get absorbed by another atom and re-emitted. So there's this constant changing of photons. So some photons get absorbed and they get re-emitted. So it's not the same photon, but we can imagine it's a photon caused by this chain reaction. So the photon is produced at the center of the sun. It hits an atom, produces a chain reaction, produces a photon, which will then hit another atom, and so on and so on. This chain reaction itself is going to take between 1,000 and a couple of million years to actually get to this edge of the sun, to the point where it can start traveling freely through space. The reason it takes so long, imagine if you're just in a crowded room. I know that's scary in COVID times, but you're in a crowded room and you want to walk to the other side, but you don't exactly know where you're going. So you just start randomly walking in any direction. The idea is anytime you bump into somebody, you turn around and change direction. You walk a bit more, you bump into somebody else, you change direction. You keep doing this. Eventually, you will be able to cross the room, but there are lots and lots and lots of interactions, as David just said here in the comments. So you walk a bit, you bump, you walk a bit more, you bump. This is what the photons have to do to escape from the inside of the sun. So even though we say that when you're looking at the sun, or when you're looking at light coming from the sun, you're seeing photons that were produced in the sun 8.5 minutes ago. That's not actually true. You're seeing photons that come from a chain reaction that started thousands or millions of years ago, depending on how many interactions, at the center of the sun. And it took several thousand years at least for this chain reaction to kick a photon out of the sun to the point that it can then take its 8.5 minute journey towards us. So is it more right today it takes thousands of years for the energy generated to reach us? Yes, that is a great way of putting it. So these photons carry energy. These photons are particles of light. They carry a specific amount of energy. And the energy that's coming towards us takes thousands of years from when it's kind of released from different processes at the center of the sun. Takes thousands or even millions of years. We're not completely sure on these numbers. It's between 1,000 and 1,000,000, quite a range there. Takes at least 1,000 years for this to gradually come out to the point where it can kick a photon, particle of light, so that it can travel towards us. And this actually brings me to, so that was fun fact number 1. When you look at the sun, it's number 2 by now. So it will take you quite a while. It takes 8.5 minutes for this photon to travel from the sun towards you. But this photon is already on a journey that started thousands of years ago at the center of the sun, gradually getting absorbed, re-emitted, until it can actually kick out of the sun. If the sun is shut off, will it still emit light for thousands of years? It depends what shuts it off. Now, usually when we talk about shutting off the sun, completely hypothetically, of course, what we mean is that all of these interactions stops, like everything just stops. So if the sun stops producing energy in the core, as David is saying exactly here in the comments, if the sun itself only stopped producing energy in the core, so we only switch off the center of the sun, it would take 100,000 years to reach us. However, if you stop all possible interactions, so you make the sun just stop interacting, it's not something we can physically do, but hypothetically, we just stop all interactions within the sun, you will still see the sun for 8.5 minutes because the last photons on the surface, not on the surface, the last photons on the edges of the sun still need to do their journey towards us. So depending how you shut off the sun, either you just stop the reaction, the production of energy at the release of energy at the core, in which case you will still see the sun for 100,000 years approximately, or you turn off the sun entirely, and then you would only see it for another 8.5 minutes. It's probably a good idea if we don't just switch off the sun. The sun is kind of useful for us. We should probably leave it on. Another thing that we can say here about the sun and about all stars is that stars do not have a surface. In the same way, we can stand on the surface of the Earth. We are standing on the surface of the Earth. We can stand on the moon. One day, hopefully, we'll stand on Mars, maybe even Mercury or Venus. These are places where we can stand. You could never stand, even if you were able to somehow survive the heat. There is not a solid surface that you could stand on the sun. The sun is a big burning ball of plasma. Yeah, they did that in Star Trek, so it's definitely physics. Yeah. I think with Star Trek, with a lot of sci-fi shows, my mentality is to always assume that the sci-fi show takes place in a different universe where the laws of physics are slightly different, because then I don't need to complain about all of the wrong physics they're throwing at us. So in whichever universe Star Trek is based, I'm sure they have their own laws of physics where they're allowed to do that. Unfortunately, in our universe, we're not allowed to do that. There is no surface to a star. It is a big giant ball of plasma. It also means defining the edge of a sun or of a star is actually quite hard. Like, where does the sun stop? Because as I mentioned before, you have these constant interactions. So you have these photons bouncing off everywhere, and at some point they're going to get close to the outer ring or the outer layers of the sun, at which point they can start gradually coming out. But it's not really a solid surface. You wouldn't notice it other than burning up. Assume you're immune to the heat somehow. If you try to get close to the sun, you wouldn't hit a big ball of plasma. You wouldn't notice when you wouldn't physically have an object stopping you from entering the sun. There isn't a surface there. There is the heliosphere around the outside, as Luke just mentioned here, which is kind of the outmost layer of the sun, but it is not a surface. So you could never stand on the surface of the sun or on the surface of any star, because stars do not have surfaces, which is kind of cool when you think about it. Yeah, I am named after Star Trek characters, so I do kind of need to just evolve with whatever physics Star Trek throws at us and try to make sense of it. So I just assume it's a different universe. Makes it easier. Yeah, as David is saying, we do have kind of the informal edge of the sun, which we say this is kind of where it starts and stops, which is the photosphere. But yeah, there's not actually a specific solid surface to any star. You definitely need new shoelaces. Yeah, you'd probably need new shoes. You'd get kind of burnt if you tried to go there. Okay, but let's move on from the sun. This was just a few comments about the sun. We wanted to go find our first planet. So we need to travel a while. Pretty empty, as you can see, pretty empty. So far we've traveled nearly 30 million kilometers. We haven't yet found the first planet. So we can carry on going, carry on going. It's a lot of empty space here, and here we have our first planet. We have traveled 58 million kilometers. So remember here that the moon is 1 pixel, and every pixel that I'm scrolling corresponds to about 3,500 kilometers. So we've traveled 58 million kilometers, and we found Mercury, which you can barely see on your screen. It's just a tiny, tiny dot with the arrow is pointing. And I'm not sure how much you can read the writing at the bottom. It might be a bit small. So I just want to show you here, another cool thing about this page is that you can actually change the units. So we found Mercury about 58 million kilometers away. Planets are less exciting than the sun. Depends on the planet. Your favorite planet after Earth? Mercury is a really cool planet. I know why you like it though. Of course, it's Mercury. Of course, how can you not like it? So you can change the units, I was saying. So currently we have it in kilometers. You can also put it in pixels. So we've traveled 16,000 pixels because we're using pixel as a unit of distance here. 16,000 pixels. But these are units that are quite difficult for us to imagine. But something that we can all imagine, for an example, is a bus. So currently, I'm not sure if you can read these numbers here at the bottom of the screen, but we are now 4,600 billion buses away from the sun. So you would need 4,600 billion buses stacked side by side to reach Mercury from the sun, which is a ridiculously huge number. You can also, if you want, see this in Great Walls of China. We would need 6,000 times, 6,500 times the Great Wall of China to go between the sun and Mercury. I'm not sure if visualizing like 6,000 billion buses is easier than visualizing 58 million kilometers, but sometimes it is. You can also do it in blue whales. If you know the size of a blue whale, we can do this in blue whales. So you would need, let me just count my zeros here. We have 3. You would need 1.9 billion blue whales to cover the distance between the sun and Mercury. You probably don't want to do that to the whales. I don't think the whales would appreciate being used in space to measure distances. But this web page also provides these cool units just to help us visualize things a bit. Dead blue whales, yeah. Don't think these whales can survive in space, so you probably don't want to throw them all out. Unless if you peel them carefully. Yeah, maybe you meant pile them there, because peeling blue whales just sounds a bit weird. But yeah, to our knowledge, these space whales would not survive. Not that we know of any space whales, of course, in the world of Doctor Who. There are star whales, but not that we know of any space whales. But if you wanted to, why do I get a nan now? That's funny. A whale space would not last long. No, yeah. Yeah, you probably don't want to take your your animals out to space with you. Okay, so we found Mercury, we found the first planet. Let's try to find the second planet. And now I'm going to set it to travel, this nice button here, travel at the speed of light. So we're now going to imagine we're a particle of light. And this is how fast light travels. And you can see that this is actually pretty slow. So I'm not going to keep up this speed because it would take us another about 7 minutes to reach the Earth. So I'm not going to keep up this speed. So let's just carry on. Oh, I switched to light minutes. Can we go back to kilometers? So let's go and find Mars. There's some text along the way, but we're still just scrolling. Not Mars, sorry, Venus. Venus is the next one, of course. Still scrolling. I know it looks like I'm not doing anything. I hope you're paying attention to the scale at the bottom of the screen that is moving down here, because else it just looks like you're staring at a black screen. Okay, we found Venus. You can see Venus occupies about 3 pixels on the screen. Venus is about 3 times the size of the moon. And by now we have traveled 108 billion kilometers. Sorry, 108 million kilometers. Yes, 108 million kilometers. And we have found Venus. second planet. Now, Venus has quite a few cool things. Despite not being the closest planet to the sun, it is actually the hottest planet in the solar system because it has a ridiculously thick atmosphere that traps all of the gases of the planet. It has the biggest greenhouse effect you can imagine. It has this ridiculously thick atmosphere. You're following along on the webpage. Awesome, that's great. This website is amazing. I posted the link in the comments if anybody wants to follow along. Please do so. It's great fun. And it really, when you see me scrolling, it might not seem so much, but when you're the one scrolling, your hand will get tired, believe me. Space is big. It is. It's really, really, really big. This is the idea of this slide. We're still in the solar system. Thank you for posting the link again for anybody who hadn't yet seen it before. Thanks, David. I appreciate that. Okay, so Venus has this ridiculously thick atmosphere. It's ridiculously warm. It's kind of about, I believe, 500 degrees Celsius on the surface of Venus. It's a ridiculously hot planet. Interestingly enough, billions of years ago, we think Venus actually had water. So our current best guess is that a couple billion years ago, Venus looked very similar to the Earth, with water, with oceans, maybe even with some type of life form. We don't know. We haven't found anything there yet. The biggest problem being that we don't really have much technology that we can send to Venus. We've tried in the past, and our spacecraft basically melted within a few minutes. So yeah, Venus is kind of hot, kind of uninhabitable, to the best of our knowledge. Thank you for the Appreciate Award, David. I appreciate the award. Yeah, feel free to bring Hitchhiker's Guide to the Galaxy quotes. And, I am a big sci-fi nerd. Any quotes you want to bring from Doctor Who, from Star Trek, from Star Wars, from Hitchhiker's Guide, Babylon 5, Firefly, bring all the sci-fi quotes. I am happy with this. I am happy if you turn this into a sci-fi quotes area. So one thing that you might have heard about Venus is that on Venus, it rains sulfuric acid. Now, sulfuric acid burns through any living matter and any metal, pretty much. It is one of the most corrosive acids that we know of. And on Venus, you actually get sulfuric acid rain. The atmosphere is so dense, and it has all of these ridiculous amount of sulfuric gases there, that there is actually sulfuric acid rain constantly. Russia did manage to get a few missions there and a few pressure snapshots. Yeah, we do have a few small, great images of Venus before the spacecraft melted. So we have been able to land on the surface of Venus, but the things we send there don't last long. We've been able to take photos from orbit. You don't see much. You just see this huge atmosphere. It's kind of difficult to see through it. But we have been able to land things on the surface of Venus, and I think it lasted about 13 minutes before it got burned up. And a balloon in the atmosphere, that was really cool too. We also had a balloon in the atmosphere. Also didn't survive long. It's a problem with Venus. But despite the fact that there is sulfuric acid raining down on Venus, it actually never reaches the ground. If somehow you were able to get to the surface of Venus and you're somehow protected against the ridiculous heat and all of the stuff around you, one thing you wouldn't have to worry about is the sulfuric acid rain, because the surface is so hot that this rain actually evaporates before hitting the surface. So it's gradually raining down sulfuric acid, but the sulfuric acid will turn to mist and evaporate before hitting the surface. So you don't really need to be worried about getting caught in a downpour of acid rain on Venus, but there is a lot of nastiness on Venus. And of course, first you need to get through this atmosphere, through to the planet's surface. Hey, Peter, great to see you here. Thank you for stopping by. We're talking about cool space facts, just talking about the fact that Venus has acid rain, sulfuric acid rain, that would basically melt anything it touched or disintegrate anything it touched. But fortunately, it doesn't reach the surface. It evaporates because Venus is so hot. Incredibly hot. Oh, thank you for the great topic award, PC. I appreciate all the awards. Thank you. So, Venus, very hot, very inhospitable, not very friendly planet. It's a nice planet. It has a thick atmosphere. It's pretty cool. But you probably don't want to go to Venus anytime soon. Okay, we found Venus. So now we keep on scrolling. We know the planet that's coming next. We keep scrolling, lots and lots and lots of empty space, and then we get this nice message. We're halfway home. There's not enough buses to get us there. Yeah, definitely. I mean, by now we're halfway between the sun and the earth. We've only traveled half of the journey, halfway home. 470 degrees on the surface of Venus, 92 times the pressure of our atmosphere. Exactly. Short version, do not go to Venus. Okay, so we're halfway between the sun and the earth, and let's see how many buses we need so far. It's a lot of buses. Let me count the zeros here. 1, 2, 3. It's 10 to the 10. So that should be 10 billion buses. We need 10. You always have to count it like that, sorry. So we need 10 billion buses to get us halfway to the sun from where we are. I don't think we have enough buses. How many whales would we need? Let's see. How many blue whales would we need? We would only need 4 billion blue whales to get us there. I say only. But still, we would only need 4 billion blue whales lined up one next to each other to get us halfway to the sun. Okay, let's carry on and see when we find Earth. Keep scrolling, keep scrolling. My hand's going to get tired. Okay, Earth, Moon. Hey, Knowledge, nice to see you. Thank you for stopping by. Okay, we have found the Earth. More buses than people. Yes, by now we've used up all the buses and more. We don't have enough buses to do this journey. So we found Earth, we found the Moon. As we know, for now, Earth is the only planet we found with actual life forms. But yeah, the space whales, when you try to line up blue whales to get to Earth, they just go off and do their own thing. Whales are so difficult to control. We probably shouldn't use blue whales to map our journey between Earth and the sun. So we are now, let's keep it in kilometers for now, we are now 1 astronomical unit away. 1 astronomical unit is the very nice measurement that we've invented, which is, for some reason, it's giving me a nan. Don't like nans. Okay. 1 astronomical unit is approximately the distance, or is defined to be the distance between the sun and the Earth. So we're 1 astronomical unit away. Now, in kilometers, this is 150 million kilometers. 150 million kilometers. Okay, I keep having to mentally count the zeros here. It's like we have 6 zeros, 150 million. Else these numbers are too big to read. So 150 million kilometers from the sun, and we have found Earth. So now we need to go to the next big planet. Next planet is going to be Mars. Mars will take us a while. Mars requires substantial amount of scrolling to reach. So I really hope you're getting an idea here of how much of the universe is just ridiculously empty. We're still only on the solar system. And then we get this nice message. Imagine we're doing this journey from the sun. We're going out. We're trying to find Mars. It would take about 7 months to travel this distance in our best spaceship. So it takes quite a while to do these journeys. And for comparison, in case you wanted to know this, if you wanted to keep movies or watch your favorite sci-fi shows to keep you entertained, you would need about 2,000 feature-length movies to occupy this many waking hours in 7 months. So you need a lot of films to keep you busy here. Yeah, let's just go back. So you just made a great comment there, David, that I actually will come back to later. But as you mentioned it, let's go back. Because you brought it up, David, we'll go to it now, and then we'll come back later. David just made the very great comment here of notice the distance between the Earth and the Moon compared to both the Earth and the Moon's size. And the Moon is 1 pixel here. And the distance between the Moon and the Earth is quite a few more pixels than that. So, we see the Moon as being pretty close, but it's actually really far away. I compare it to the size of the Earth, it's really, really far away, which to me kind of makes it even more incredible that we've actually been able to go there, because this is not an easy journey. Space is empty. There's a lot of stuff that can go wrong. And, this is really just throwing a rocket at a tiny target and hoping we hit this tiny target that's very far away. And somehow we keep managing to do this. Well, not currently. Haven't been to the Moon in a while. We really should go back to the Moon. Okay. Now we're still 30 Earth diameters away. Thank you, David. It's great to have you here because I don't have all of these numbers written down. So it's great that David is here in the comments. For anybody who doesn't know, David Dunn is an astronomy professor and does amazing broadcasts with more called Space Facts. So basically any numbers that David quotes here in the comments, I absolutely believe him. Don't bother. You can fact check it if you want. I'm not going to. I'm just going to assume that all the numbers David is quoting are absolutely correct. Okay, we're still looking for Mars. We're still scrolling, still scrolling. It was going to take me quite a while to scroll through all the solar system. And we have found the red planet. 228 million kilometers from the start of our journey, we have found the red planet. Again, only 2-3 pixels big here. It's also pretty small. So how many buses have we used by now? We are now at, let me get this right, 18 billion buses. We need 18 billion buses to get us all the way between the sun and Mars. So, Andy, I see the comment you've just made there. That's spoilers because we are coming to that later. Trillion. It should be billion, right? Let's see. This would be 18 million. This should be billion. Yes. Yeah, teaching astronomy helps you keep these numbers. Yeah. For me, so I am a cosmologist. I study the universe. And things like this are what we call really like small scale. So obviously what I'm showing you here is the solar system is ridiculously big. But usually I'm focused on things like galaxies or how all of these thousands of galaxies fit together. So these numbers are really local, small scale for me. So they're not numbers that I use regularly, and they're not numbers that are in my mind, which is why I have to check the numbers here on my screen. Of course, David, you teach astronomy, so these numbers, you have to know them, absolutely. So yeah, as I said, do follow David here. I'm glad you're here in the comments to help me out with these numbers, David. Okay, yeah, billion. And I should mention here, as you just mentioned, trillion versus billion, I am always using the scale where a billion is 10 to the 9. So 1 billion has 9 zeros after it. Some countries actually use a different definition of a billion. This is known as long scale versus short scale. In Spain, for an example, 1 billion is 10 followed by 12 zeros instead of 9 zeros. So there's that in German also. So there's actually a bit of distinction we need to make when referring to billion. But in most English-speaking countries, billion is 1 followed by 9 zeros. So when I'm talking about billion here, I'm always counting 9 zeros. Thank you, Heavenly, for the Super Heart Award, and thank you, David, for the Got Talent Award. I really appreciate it. Okay, so we have found Mars. Before we go on, Mars is a great planet. You know, Mars, it's our neighbor. We want to go to Mars at some point. If you want to know about all the cool things that used to happen on Mars in terms of water, I did a broadcast recently about hoping to find water on Mars and water elsewhere in the solar system. So if you want to know more about water on Mars, do check out my recent broadcast. But I want to show you something else that's really, really, really cool about Mars. And in fact, let me just take away this particular scale thing that we're doing, which is going to take longer than planned, and bring up this image here. So this here is a real image taken from the surface of Mars, and it's a sunset. You are looking at a Martian sunset. This image was taken by the Curiosity rover in 2015, and this is a sunset on Mars. This is real color. This is not a doctored image. This is actual color of what a sunset would look like on Mars. And of course, sunsets are something that we're used to. You might also notice that the sun looks slightly smaller than what we're used to because it's further away. So sunsets are something that we're used to, and we're very much used to sunsets being red or orange or these very pretty colors. Now, sunsets on Mars are actually blue. It's amazing, right? We have this sunset. This is an actual picture of a sunset on another planet. And here's the thing. So thank you for the WOW award, David. I appreciate it. So we're used to the idea here on Earth that during the day, the sky is blue. I'm sure anybody here who has kids has probably been asked at some point, why is the sky blue? And you have to figure out the answer to that question. Why is the sky blue? We know the sky is blue. We know sunsets are orange and red. And yet on Mars, it's the complete opposite. During the day on Mars, the sky is red. The sky is almost reddish-orange constantly during the day. And then during sunset, the sky is blue. The sky turns blue. And my throat is rather dry. I didn't think I had hay fever allergy type thing, but this weekend I've been in the countryside and I feel like I've developed some allergies to something, so constantly sneezing this weekend. Why is the sunset on Mars blue? This is a great question. This is a question we should be asking ourselves. So before we switch to Mars, let's just remind everybody why the sky is blue on Earth. Now we know that the sun emits light in every possible color. The light from the sun covers all the range of the electromagnetic spectrum. In fact, let me just bring up this image as well. Now I want to go to side-by-side view. And maybe I just take myself away for a minute here. Okay, electromagnetic spectrum here on the right. As a reminder, just in case you don't know this, blue wavelengths, blue light has very, very small wavelengths, red light has very big wavelengths. The light emitted from the sun comes at us with all these different wavelengths. The wavelength of a specific photon determines the color that our eyes interpret it to be. So we can go anywhere from ultraviolet purplish blue to red on the opposite end. Blue has very short wavelengths, red has very long wavelengths. Now, the light that comes from the sun, as it travels through the atmosphere, is going to be scattered off of the particles suspended in our atmosphere. Our atmosphere has a lot of gases and a small amount of dust. The particles coming in are going to, the particles of light, the photons coming in, are going to bounce off of all of these atoms, and they're going to be scattered. Now, within our atmosphere, blue light, small wavelengths are scattered more efficiently. That means that this blue wavelength, when we say scattering, what we just mean is that the particle of light has changed direction because it bounced off of something. I'm doing hand gestures, and just remember that you currently can't see me. So a particle of light hits an atom or a molecule, it changes direction. So when I say scattering, I just mean changing direction of these particles of light. Now within our atmosphere, blue light can be scattered more easily. The reason being that the atoms or the molecules within our atmosphere are the approximate size or are closer in size to blue light than they are to red light. Particles scatter more efficiently when their wavelength is of the same size. Photons, particles of light, scatter more efficiently off of other objects when these objects are the approximate size of their wavelength. The particles in our atmosphere, or the molecules in our atmosphere, are closer to the blue end than they are to the red end. This means that blue is very efficiently scattered in our sky. So it can move, the blue particles of light, the blue photons, can move over a large area. They disperse, they scatter, which is why we mainly see the sky to be blue. Now at sunset, the sun is slightly lower in the sky, and it has to travel through more atmosphere to reach us. This is known as Rayleigh scattering. Thank you, Abyss, for your excellent comment there. And hello, Abyss, nice to see you. Hi, Vanita, thank you for joining. In Hindi, we say chand for moon. Thank you for teaching me that. I did not know that, and that is a really nice word. You know, I am always happy to learn space words in other languages, so really do let me know what the moon is called in your own language, because I'm very happy to learn that. Okay, so during the sunset on Earth, the sun has to travel through more atmosphere, which basically means by the time it reaches us, the blue photons have already scattered, they've already gone away, and what you're left with mainly is orange and red photons. So the reason sunsets look red or orange on the Earth is because you're traveling through more atmosphere. All of the blue photons are kind of scattered away by now. All that's left by the time it reaches you is the reddish-orange glow. So sunsets, sunrises on Earth are going to be reddish-orange. And in fact, the sky is blue just because our eyes don't pick up these kind of violet colors. If our eyes were sensitive to violet, the sky would actually appear violet to us and not blue, which is also a fun fact. There are many songs they sing in Bollywood all related to the moon. That's really, really nice to know. You know, I love listening to songs. I do like understanding the lyrics, so it's nice to know what some songs are talking about. Okay, so back to this amazing photo, which as a reminder is a sunset on Mars, an actual picture of the sun setting on the planet Mars that we've been able to take with one of the robots that we sent to Mars. Absolutely incredible. Now, Mars's atmosphere, Mars has an atmosphere. It's a lot thinner than ours, but Mars does have an atmosphere. Throughout the entire atmosphere, there is a lot of oxide. There is a lot of basically rust. Iron oxide, which is rust. Iron oxide, yes. There's basically rust, which is what gives Mars its reddish-orange color. The whole surface is covered in rust. The whole air is full of these rusty dust particles of rust, basically. Now, these rust particles are larger than the molecules within our own atmosphere, which means they are going to more efficiently scatter the larger wavelengths, which are the red wavelengths, ferrous oxide, thank you, ferrous oxide, which is ferrous, yes, of course, ferrous oxide. have iron oxide. So you have rust in the atmosphere. I always forget the chemical names for these. These particles of rust, these molecules, are larger than the molecules we have in our own atmosphere, which means they're more efficiently going to scatter the red photons. So, in the same way that we know the sky is blue on Earth because of the way it scatters, the atmosphere on Mars, the sky on Mars, will appear red. Iron oxide has few forms, FeO and Fe2O3. Yes, it does indeed. It has a few forms. Please don't ask me which specific one there is on Mars. I got as far as rust. Let's leave it at that. Iron oxide. Okay, so because these particles of iron oxide are larger than the ones within our own atmosphere, or the gases within our own atmosphere, it's more likely to scatter, or it's more efficient at scattering red. So the same mechanism that makes the sky appear blue on Earth is what makes the sky appear red on Mars. And then you have the same process happening at a sunset. During a sunset, the light from the sun has to travel through a thicker layer of the atmosphere, which means by the time it reaches you, all of the red photons have been used up, and the only ones that can reach you are the blue photons. So the exact same mechanism that lets us have blue skies and red-orange sunsets here is the exact same mechanism that means on Mars you actually get blue sunsets and red skies. And this is something that I think is really missing in a lot of sci-fi shows, even Interstellar. Interstellars, for some things, a very nicely done scientific movie, for some things. There's other things that they kind of miss a mark on, but for some things it's really good. In Interstellar, they go to 3 different exoplanets, 3 planets outside our solar system. And in every single one, the sky is blue. Because it is on Earth, but that doesn't mean it's blue on any other planet out there. A lot of you have probably wondered what would it be like to walk on another planet. But have you thought what would the sky look like on another planet? Because depending on what gets absorbed in the atmosphere, or depending what particles are in the atmosphere and what scatters, the sky would be a different color. The sky on Mars is red, sunsets on Mars are blue. Another fun fact is that on Mercury, all colors are absorbed because Mercury has no atmosphere, which means on Mercury, the sky is actually black. So that's also fun. If you go on Mercury, the sky would appear completely black and you'd see the sun about 3 times bigger than what we're used to seeing it. So anytime you think about walking on another planet, you now have to ask the question of what color would the sky be on this planet? Would it be blue on any planet we can breathe on? That is a really, really, really great question, David. So let me think about that. It very much depends, because to breathe we need mainly oxygen. But our atmosphere also has a lot of nitrogen, it also has a lot of carbon dioxide, but too much of that. It has a lot of different things. So I'm not sure if you'd need the exact same composition. So I think you'd be able to breathe in atmospheres that have a slightly different composition, and I'm not sure if this composition would be different enough to affect the color. It might be. So I really don't know. I'd have to do the calculation for that. But I would guess that you could have a planet where you have the right amount of oxygen to be able to breathe, but where you also have other gases or other particles in the atmosphere that divert the light more. So I don't think they necessarily go hand in hand, that a breathable atmosphere means that the sky would be blue. I don't think they necessarily go hand in hand. Fun fact from Abyss, the sun doesn't emit more violet light, but if it did, the sun would say blue giant, the sky would be violet. Yes, Abyss, just before you joined, I actually made the comment that if we were more sensitive to violet light, the sky would actually be violet to us. But yeah, Mercury, though, if you're still here, you would probably like that comment as well, that Mercury, apart from being called Mercury as an awesome planet, it has a super goth sky. It has a black sky with a huge sun. Mercury is a nice planet to visit. Black Sky, hey Lisa, nice to see you. Thank you for being here. Great to have you in the comments as well, Lisa. Okay, so we've made it to Mars. It's taken me 50 minutes already. Wow, we're going to have to speed this up because we're going to be here all evening else. Let's bring up our cool thing back on the screen here. And let's put it back in picture-in-picture. Thank you for the Mind Blown award, Lisa. I really appreciate the award. Okay. So this webpage was, I just closed my Happs window and it's back. Bit hot if we visit Mercury? Yeah, it's going to be a bit hot on Mercury. It's definitely not a hospitable planet for us. Okay, so we found Mars. We've gone 18 billion buses, 18 billion buses from the sun. I realized we still had the unit up. 18 billion buses from the sun. We found Mars. Great. We found the first 4 planets. And again, there's been a lot of scrolling through a lot of empty space, and I'm not sure if you can see it down here, how far my scroll bar has gone from the left versus how much it still has to go to the right. And this is only the solar system. Thank you again for posting the link. So for anybody who's just joined recently, David keeps posting the link to this webpage that we're using. Do check it out, it's great fun. And then you can really get a feel for how much we're scrolling here. Black Sky reminds you of Snow Crash, a Neil Stephenson novel. I have not read that. That will go on my ever-increasing list of books to read. Thank you. Okay, and as we start to travel away from Mars, we get this nice comment here saying, sit back and relax. Jupiter is more than 3 times as far as we have already traveled. So it's taken me about 50 minutes so far to get to Mars. This is a ridiculously long time. I am not going to scroll all the way to Jupiter. Instead, I'm going to use nice buttons at the top of my screen here to skip ahead to Jupiter. Now it's going to accelerate. We're going to travel a lot faster than the speed of light, but let's zoom off to Jupiter. You can see it's accelerating. Hopefully you can see at the bottom of your screen how fast this is going. We just accelerated over to Jupiter because I did not want to scroll that much. Jupiter, biggest planet in our solar system. We just jumped ahead to Jupiter. Let me just put this in kilometers. I think we scrolled so fast that I broke the conversions down here. Can we get it in buses? Okay, we can get this in buses. We are now 61 billion buses from the sun. So again, this comparison is just if you take the average bus and you pile up buses between the sun and Jupiter, we have now used up 61 billion buses to travel. There are not this many buses. Hypothetically, we have used up 61 billion buses to travel between the sun and Jupiter. Can I get this in blue whales? I like my units in blue whales. We will miss all the clever comments along the way, which is why I really encourage you to go back and check over this page yourself, because there are a lot of cool comments on the way that I'm skipping by because I do not want to scroll infinitely. Okay, so we are now 25 billion blue whales away from the sun. So we started at the sun, we're traveling towards Jupiter. 25 billion blue whales are needed to cover the distance between the sun and Jupiter. We don't have that many blue whales, and as we've already mentioned, blue whales are quite difficult to get to lie in a line. They're usually going to go off and do their thing. And of course, the whales would be dead in space, and we don't want to kill our whales. Okay, 25 billion blue whales away from the sun. And you can see that Jupiter is pretty big. Remember our scale here, for anybody who's just joining, the moon is 1 pixel. So everything here is to scale, assuming that the moon occupies 1 pixel in our screen, and everything is scaled accordingly. I'd like to contract to build those buses. Yeah, you know, I'm not going to pay for those buses, sorry. Somebody else wants to finance the 61 billion buses we need, please go ahead. I will not do so. I like the units I said at NaN when traveling at superluminal speed. Yeah, we try to travel too fast, and it's just like, this is unphysical. I'm not even calculating this until you've calmed down. Okay, now let's actually get this in real units. Let's get this in kilometers. It doesn't want to convert it to kilometers for me. Astronomical units neither. So for some reason, we're stuck with blue whales. Okay, let's do it in blue whales. So we found Jupiter, and you can see here 4 of Jupiter's moons. These are the 4 Galilean moons. We have Io, we have Europa, we have Ganymedes, and we have Callisto. These were the first 4 moons observed by Galileo. They were the first objects we ever saw that didn't orbit around either the sun or the Earth. These were the first moons that we found orbiting around another planet in our solar system. Yeah, the whales would thank us for all the fish and fly away. Yeah, you know, there are a lot of sci-fi shows that call on space whales. Yeah, Doctor Who also has star whales, only one of them though. But yeah, we're currently stuck on using blue whales as our units of distance. And again, as we did when we saw the Earth and the moon, just check out the distance between Jupiter and these moons. Like you need 2 or 3, you need like 2 Jupiters to reach the first moon, Io. These moons are slightly bigger than our own moon. So Io, Europa, and Callisto are slightly bigger. Ganymede is definitely bigger than our moon. They're not a huge amount bigger. I think they're only 2 pixels on the sky instead of 1, but they are slightly bigger. As David just said, these were already discovered by Galileo back in the early 17th century. Ridiculously long time ago. And as we know, this was one of the evidences at the time that the Earth is not flat. We've known this for thousands of years. There is evidence going back a very long time for this, but this was another proof of that in the 17th century. Futurama has an episode on space whales as well. Wow. My problem with Futurama, I started watching Futurama and I got to the dog episode, and anybody who's watched it knows exactly which episode I'm talking about. And I could not get through that episode, and I have never gone back to the show. So, yeah, I have an issue with that show. Is it true humans would boil on Mars because of the pressure being 10,000 times the Earth? Yes. The cool thing is that water actually boils, not spontaneously, but even if the temperature is not so high, the pressure on the Martian surface is so high that water could boil immediately. Okay, Europa is slightly smaller than our moon, the rest are bigger than our moon. Thank you, David, for that fact. Yes, Europa does appear to be here only 1 pixel. On the topic of Europa, Europa is one of my favorite objects. Europa is one of my favorite objects in the solar system. Let me just remind everybody as to why. Now, last week, or 2 weeks ago, we had the Happs theme of Happs water, and I did a broadcast about where in the solar system can you find water. And there we discussed this amazing moon around Jupiter known as Europa. Europa has an iron core, then it has a rocky mantle, then it has an ocean going the whole way around the moon that is about 100 kilometers deep, and it has a surface layer of ice that is about 30 kilometers deep, or about 20 kilometers deep. So there is a moon, more than one, but Europa is one of the 2 moons in our solar system that has a layer of ice, and underneath the ice, 100-kilometer deep ocean. For comparison, the deepest point on the ocean that we've been able to find on Earth is 11 kilometers. On average, the oceans on Earth are about 3 to 5 kilometers down. And now we're talking about an ocean that is 100 kilometers deep, kept slightly warm by the rocky mantle and protected from the outside by this icy layer. This is one of the most likely places in the solar system that will ever find any type of life, any primordial microbial life. Europa is our prime choice for that. Yeah, it is a candidate for life. It absolutely is a candidate. The episode is called Jurassic Park. Yes, that episode really did hit home. Yeah, Jurassic Park is one of the saddest episodes made of what was supposed to be a funny show. Moving on, Europa. For anybody who didn't see my water broadcast, I am actually going to post the link here in the comments. I just remembered that I actually had that link ready. Posting link here in the comments. For anybody who didn't see my water one, please go back and watch it, because I'm not going to do Europa the justice it deserves now, because we're only about, I'd say we're less than halfway through my list of space facts for the day. Yeah, we haven't got through many of them yet, and we've been online for nearly 1 hour. I think I was very optimistic with how much I wanted to cover today. So I'm not going to go too much into detail now about Europa. If you want to know more, check out the podcast I've just linked in the comments. What color is the sky on Europa? Great question. Really, really great question, y'all. I do not know. I actually didn't think to check that. We haven't yet sent anything down to the surface of Europa, so we don't have any photos from there. Now, Europa should not have an atmosphere. Yes, Europa does not have an atmosphere to my knowledge, which means if it doesn't have an atmosphere, the sky would be black. It's great that I reached that conclusion, just as David posted in the comments, that probably black. If we both agree, it's less likely that we're wrong. So no atmosphere, the sky would probably be black on Europa. Okay, much as I love Europa, let's take it away from the screen and go back here. Let me just check my list of space facts, how we're doing. We're like a third of the way, not even a third of the way through. Oh my God. Okay, Enceladus is also another candidate for life. Yeah, but Enceladus is around Saturn and we're still around Jupiter. But let's change that. So we found Jupiter. Again, I'm not going to scroll because Saturn would be very long distance away. So let me just jump straight ahead to Saturn. And let's see when we get to Saturn. Still moving, still moving. Hey, Frankman, thanks for joining. Nice to see you here. And we have found Saturn and Saturn's rings. And Saturn, as far as we know, has about 69 moons. Jupiter also has around 70-something moons. We have a lot of moons. Maybe I could do a part 2, maybe, or maybe we just keep going because this is fun. So we're going to keep going basically as long as I'm still slightly awake at some point. At some point we'll have to stop. But for now, Saturn. We're at Saturn. Saturn has, as we know, these amazing rings, which you can see here are pretty big compared to the Moon, compared to the size of Saturn itself. 82 moons for Saturn, 79 for Jupiter. Thank you for the numbers, David. Saturn is an incredibly pretty planet. If you can ever look at it through a telescope, it's an amazing experience because you can really see the rings. And it's really cool to see this. Saturn has 82 moons, ridiculous amount of moons. The most commonly known one is Titan, which is a moon completely covered with methane. It has oceans made of methane, so Titan is also not a welcoming moon. But Saturn also has one of my other favorites, or possibly my favorite moon in the solar system, which is Enceladus. And Enceladus is also a moon that has a huge ocean underneath a layer of ice, and Enceladus actually has geysers. So what you can see here is an image taken by Cassini, where you can see these huge geysers of water being thrown out into space from this moon. You did a project on it in 5th grade, so quality bonding time. Yeah, Saturn really is such an amazing planet. It's so pretty, and it's one that we're all so attracted to because it's pretty. It has these rings, it has the moons. It's a super fun gas giant surrounded by icy rings. Really, really cool planet. But as you can see here, Enceladus, this moon around Saturn, spitting out water geysers, which actually go on to form one of the rings of Saturn. So Saturn has several different rings, and the E-ring around Saturn, where they're all named with different letters of the alphabet, and the E-ring around Saturn is believed to be formed mainly of the particles of water and ice that are spat out from Enceladus. Again, I just saw I got a Golden Squirrel Award. Thank you, Frankman, for the Golden Squirrel Award. I think that is my first Golden Squirrel, and I like squirrels, so thank you for that. Is it also true that we don't quite have the tech yet to make spacesuits? Yeah, spacesuits handling the Martian surface is pretty difficult, actually. Part 2 will be about planets around the Proxima Centauri. Yeah, that would also take me quite a while. The International Space Station suits handle zero pressure, as did the moon suits. Thank you for that comment, David. I was just slightly distracted from that, but yes, thank you. Yeah, geysers on Enceladus are absolutely amazing. Your PhD thesis was about the rings of Saturn, David. That is absolutely amazing. That is really, really cool. I think that's something that a lot of people can maybe understand a bit more, like Saturn's rings. We all can think about this. In my case, I did my PhD about dark matter, which is something nobody can see. Makes it a bit hard to think like, I spent several years studying something that we can't see, but it was fun. So yeah, geysers on Enceladus are amazing. I believe they don't produce all of Saturn's rings, only the E-ring. The other rings, I'm not completely sure what specifically produces them. It's a combination of asteroids and comets and other things within the solar system, but only the E-ring is produced by the geysers here. Okay, we're speeding up a bit because it's going to take us a while. Let me just check my list. Where are we? Okay, we are. So this thing about Enceladus was my 7th entry on my list. We've only done 7 official space facts so far. This is 7 out of 19, by the way. So yeah, let's get back to speeding through the solar system. How do you know you're studying dark matter if you can't see it? Yeah, we can't see it, so I spent quite a while writing like, how can we study it if we can't see it? How do we know it's there? My PhD thesis is publicly available online in case anybody wants to check it out, but yeah, you don't need to do that. Okay, we found Saturn. We've traveled, how many blue whales have we traveled by now? 47 billion blue whales by now. So we're using quite a few blue whales to travel these distances. Okay, we have done Saturn. Let's move on to the next planet in the solar system, which Jupiter, Saturn should be this one, everybody's favorite planet to make jokes about. We're speeding away, speeding, and we have found Uranus. The ABC main rings around Saturn were produced by an object that broke up when it got too close to Saturn some 100 million years ago. Thank you, David. That's actually what I had in mind. Thank you for confirming that. Do any of the other gas giants have rings? Yes. Actually, Jupiter has a very small ring system. Neptune has rings, and I believe Uranus has rings as well. Maybe David can fact check me on those as well. But yes, Uranus and Neptune have rings. Neptune actually has really pretty rings, and Neptune is pretty much on its side. So the rings are tilted. Correct, yes. Okay, so Uranus, everyone's favorite planet to make jokes about. It's a blue giant. It's kind of gassy, as you'd expect, given the name. But as you can see, it's not as big as Saturn. It's not as big as Jupiter. But there's one cool thing about Uranus. So Uranus is the one that's on its side. So most planets spin kind of like this around the sun. Uranus is tipped on its side. Jupiter, Saturn, Uranus, and Neptune all have rings. Yes, those are the ones I listed. Perfect. So Uranus is on its side. We are accustomed to having different seasons here on Earth, right? Where we have usually 3 months of winter, 3 months of spring, 3 months of summer, 3 months of autumn. This is the cycle we're accustomed to. Now, seasons on Uranus are actually pretty messed up because the planet is on its side. So instead of spinning that way, kind of like a spinning top, it's spinning that way, which is cool. This means that seasons on Uranus actually last around 21 years. So you get 21 years where you have a bit of night and a bit of day. Then you have 21 years where I'm assuming you've picked a specific spot on Uranus and you're sat there enjoying Uranus seasons. Then you get 21 years of absolute darkness, 21 years of winter, absolute darkness. Then you get another 21 years where again you have a bit of light, a bit of dark every day. And then you get summer where you have 21 years of sunlight constantly. No night. Now, if you've ever had the chance of going far north to Alaska, to Finland, to these really northern countries, you know that in summer daylight lasts about 20 hours, or even the whole, if you're far enough north, the sun never sets. On Uranus, you would have 21 years of sun. That's a lot of sun. So that is a great question there, David, of why is it on its side? Why are all the other planets the right way up? So, yeah, the main reason that they all spin in the same kind of plane is because of angular momentum. So it's just the most energetically efficient way, especially when they're formed. The sun is rotating in one direction, they're moving around the sun. They're going to be spinning kind of along the same axis, approximately. I believe, to my knowledge, the reason Uranus is on its side is because it was knocked by something pretty big, probably a huge asteroid or another protoplanet that was still forming, crashed into it and actually knocked it on its side. So it did at some point spin the correct way and then it was kind of knocked over. Fun fact from Abyss, if all the planets were named after ancient Greek deities, our planet would be Hermes, Aphrodite, Gaia, Ares, Zeus, Cronus, Poseidon, and Uranus. Yes, that is true. There's also the other names for them. So there's the Greek name for them, and there was the Roman gods that were named for them as well. I'm very amused in terms of naming things that Jupiter is obviously named after Zeus, and all of the moons are named after all of Zeus's lovers. And at some point, we sent a probe to Jupiter, and it was called Juno, and Juno is named after Jupiter's wife. So we sent Jupiter's wife to check up on Jupiter and all of its lovers. Fun fact in terms of naming things. A space whale knocked over Uranus, we can't disprove that. If we're going with the idea of space whales at this point, why not? Okay, so let me just check the system, the units here. 95 billion blue whales to get us to Uranus. I'm just leaving up the blue whale unit of distance now because I think the kilometers is still broken. Let me check here. Yeah, kilometers is broken, so we're stuck with blue whales now. Let's just leave it on blue whales. Okay, so I mentioned now the seasons on Uranus lasting 21 years each. This is actually our best guess. The thing is, we've only had reliable observations of Uranus for about 50, 60 years now, which means we have not yet seen Uranus do a full trip around the sun. So we think that the seasons last 21 years. This is our best guess based on all the observations we have, but we're not completely sure. Okay, we found Uranus. We have one real planet left to go. Let's speed ahead to the next planet on our list, which should be Neptune. And we're speeding away, speeding away, speeding away. Pretty big distance, as we mentioned here. Space is huge. We have found Neptune 150 billion blue whales away. 150 billion blue whales. This is ridiculously far away. what I'm trying to convey here is just how incredibly big the solar system is and how much of the solar system is empty space. And you can see here we've scrolled a lot, or I've skipped ahead because scrolling was getting a bit tiring. And it's taken us 150 billion blue whales to travel the distance between Sun and Neptune, but we finally got here. Neptune is very, very pretty planet to see. I have actually been able to find it through my telescope. I was very chuffed about that because I didn't have a tracking system, and I was in a city and it took me ages, but I was finally able to get Neptune in my telescope. I was very happy, and then it was just a tiny dot, a bit disappointing, but I still found it. Okay, that's not a fun space fact, that's just a fun fact about my own telescope. I don't have a fun fact to tell you about Neptune. There are a lot of them, but I'm going to skip ahead because we are running out of time. Not running out of time, but let's just skip ahead a bit. So, we found Neptune, and it is not a planet, but still, let's go visit Pluto. And we're going to have to scroll for a bit more, and we found Pluto. 196 billion blue whales away. 196 billion blue whales is really, really far away. Going back, but was that the asteroid belts all too small to see on the scale? Yeah, we didn't see any asteroids because we're using the scale here, that 1 pixel is the size of the moon. Asteroids would be smaller than these pixels. So you would find the asteroid belt you would find 2 asteroid belts actually, but you would find one between Mars and Jupiter, and it did not show up here because all of the asteroids are smaller than the moon, which means they are less than 1 pixel on my screen, so they don't show up. Okay, so Pluto, as we know, is no longer a planet. I'm sorry, but this is how science works. We get new data, we update our definitions, we update the science because we get new data. We thought Pluto was a planet, we got new data. We saw Pluto was actually kind of small. We had to kick Pluto out of the planet club. Just to put it in perspective here, did Titan show up? Titan did show up. Titan, I believe, was 2 or 3 pixels big. Titan did show up next to Saturn. It was the only one of Saturn's moons that we could actually see. Titan did show up. So just to put it in perspective, because we talk about Pluto being small, Pluto is now classed as a dwarf planet, so it's a bit bigger than an asteroid, but it's really kind of just a chunk of rock there. To put it in perspective, Pluto is about the size of the United States. It's kind of small. If you compare the size of the Earth and you put Pluto next to it, Pluto is about the size of the United States. Neptune was the first planet that was found by using Newton's laws and calculations. Yes, thank you, David. That is indeed a fun fact that I absolutely should have mentioned. So Neptune was a planet that was predicted, calculated based on based on Newtonian's gravity. We predicted where Neptune was going to be in the sky, and then we found it. And this was a huge test of our understanding of gravity and orbits of planets. Neptune was the first planet that was predicted and then found. Thank you for bringing that up, David. That should have been on my list of facts. Pluto is so much smaller than I thought. Yeah, Pluto is 2/3 the size of the moon, about the size of the US. It's ridiculously small. We used to think it was a lot bigger, and then we realized that it actually has a moon, which is almost as big as it. This moon is Charon. Because Pluto has this big moon, it's actually a lot smaller than we thought. It no longer fits the definition. Yeah, I don't think you'll see Charon here on this picture, because I think it's way too small to actually show up. So yeah, Pluto got reclassified because it is just kind of small, and it is also ridiculously far away and ridiculously cold. So Pluto is nearly 200 billion space whales away, blue whales away, sorry, we're calling them space whales. Now, kilometers is still broken. We can't actually get this in any sensible unit, so we're stuck on blue whales and buses. So 468 billion buses gets you between the Sun and Pluto. Why did finding the big moon mean Pluto was smaller than people thought? That's a great question, Georgia. So the idea here is that we just had an observation of a blurry blob, and we thought, okay, based on this, this planet has cleared its immediate area around it. It's eaten up all other big objects, and therefore it fits the definition of being a planet. However, when we got better imaging, we saw that there was not actually one blob, but 2 separate blobs. So instead of being like all of this is Pluto, we actually saw this is Pluto, this is Charon. It looked like one blob before because it's so far away, and we didn't have the resolution to tell these two apart. As David just mentioned, Charon is about half the size of Pluto, half the diameter of Pluto. So it really is rather big. And one of the criteria we need for a planet is that it's cleared its immediate surrounding. Now, Charon is big, rather close to Pluto, which means Pluto technically no longer fits our definition of a planet. We used to think it was bigger because we just saw this blurry object. Then we got better images and realized it was actually two things. According to this app, Pluto is 5.9 billion kilometers away from the Sun. That doesn't sound right. That sounds low. Hey Ian, nice to see you. Thanks for popping by, and thank you for the high five award. Your kilometer scale is still working. Ah, yes, thank you. Okay, 5.9 billion kilometers away from the Sun. Thank you, David. Yeah, I forgot that you were following along here. For some reason, at some point, my kilometer scale broke, and I am actually amused at that because we're stuck with blasters and blue whales. So, why does Pluto look like the Death Star? I don't know. I guess you'd have to bring up Pluto and ask. Actually, I think there is a moon around Saturn. What's this moon around Saturn called? I always forget the name. Iapetus. There is a moon around Saturn called Iapetus, which actually looks even more like the Death Star than anything else. So at some point, Google photos of Iapetus. It looks like a Death Star, and it is this moon that is just sat there around Saturn. Really, really cool. Okay, so Pluto is 5.9 billion kilometers away from the Sun. It is a lot of space whales away from the Sun. We have used up 196 billion space whales just to get us to Pluto. Blue whales. We're using space whales and blue whales interchangeably now. Okay, Mimas looks like a Death Star. I think Iapetus does as well. So is Charon a bigger percentage of the size of Pluto than our moon is of us? Yes, absolutely. So Charon, if you consider the combined system of Pluto and Charon is 33% of the system, approximately. I'm just doing an approximate calculation here. Whereas we are a planet despite having a big moon, because for one, the moon is considerably smaller than us. It's a main thing. The moon is considerably smaller than us, whereas Pluto and Charon, there's only like a factor 2 difference between them. Okay, our moon looks fairly Death Star-y. Yeah, some of them do. Iapetus is a two-tone moon. Iapetus is a really cool moon as well. I wouldn't have time to explain all of the cool things in the solar system, but one of the main idea of this journey we've been taking is to really convince you that the solar system is mostly empty space. You know, we'd need 200 billion space whales to get the distance between the Sun and Pluto. The solar system is ridiculously big, and I hope this journey through this webpage has convinced you of just how ridiculously big the solar system is. But despite that, the planets themselves do not occupy so much space. Most of the solar system is completely empty. And now I'm going to come back to a comment that one of you made in the comments before. I believe it was Andy, and slightly spoiled where I was going now, which is despite the fact of how big the solar system is, you could actually fit all of the planets in the solar system in between the Earth and the Moon. No, don't worry, Andy, I appreciate it. It was a great comment to make. It was one of my cool space facts, so we get to it now. So what I'm showing you here is an illustration of how you could fit all of the planets to scale in between the Earth on the left and the Moon on the right. Now here there are a couple of assumptions. The first one is that this is when the Moon is at its furthest from Earth, which happens once a month. And as you might notice, Jupiter and Saturn have been flipped on their sides because they're kind of fat planets. Due to gravitational forces, they're slightly squashed at the top and round around the sides. So we have to flip Jupiter and Saturn on their sides, but then we can fit all of the planets in between the Earth and the Moon. Thank you for the wow award, David. Really appreciate it. Not to mention the Oort cloud, which is also ridiculously large. Yeah. So, yeah. You know, we think the solar system is huge. We just went on this amazing journey that took us ages to scroll through the whole solar system. Most of it was just blank. There was nothing. And if you take all of the massive or the most massive objects in the solar system, obviously not counting the sun here, you could fit them all between the Earth and the Moon. Thank you for the Appreciate Award, and thank you for the Toilet Paper Award. I really appreciate the awards. Seems remarkably close fit. Coincidental? Yeah. I think you have about 2,000 kilometers to spare on the right-hand side. And the person who made this illustration even threw in Pluto for the nostalgic people. And I should mention, it's shown here on the screen. This image is made by James O'Donoghue. He's worked at NASA. He's now, I believe, at JPL. Does amazing illustrations and images really to convince you of the size of things, the scale of things. I've shared some of his images before. If you like these images, please do give him a follow on Twitter. Handle is PhysicsJ. He also has a YouTube account with super cool images. And apart from the scale here of all the planets fitting between the Earth and the Moon, underneath you can see the rings of Saturn. So what we've done here is we've taken the rings of Saturn and just unwound them, laid them flat, so they're usually a ring, cut them open, you lie them flat. And you can see that the rings of Saturn, even the smallest ring, which will be the one at the bottom, the one closest to Saturn, is longer than the distance between the Earth and the Moon. Saturn's moons are ridiculously big. And they're also ridiculously thin. I think the comparison is if you shrank, let me get this straight. If you shrank the rings of Jupiter down to be the width of a razor blade, so the width of a razor blade, they would be 3 kilometers big, 3 kilometers long. So you shrink them down so they're the width of a razor blade. To scale, they would be 3 kilometers long. It's ridiculous. And as you can see, all of the rings, even the smallest one, are larger. If you unravel them, they're larger than the distance between the Earth and the Moon. Pluto is a seat filler at this point. Yeah, Pluto is just here for the nostalgic people. It's really just here just because there's a bit of a gap, so why not throw Pluto in? But yeah, we've seen the solar system is ridiculously big, and most of it is completely empty. The Earth was only a couple of pixels big in our image before. Most of it was just empty space. And you know, every life form that we know of, every species we've ever discovered, every type of life we know is here on Earth, on these tiny little pixels in the solar system. Absolutely amazing. And I hope I've made you all feel kind of small in the solar system, because that was the plan. And this is not where we stop our journey, because we're only about halfway through my fun fact sheet. Actually, we did one that I changed the order on. So we just covered our solar system, which is one star with 8 planets, a couple of dwarf planets, hundreds of moons. It's big, but you know, also if the rings were the size of a sheet of paper, the paper is too thick to represent the rings. Wow, that is really, really cool, David. Thank you for that. Wonder if it has something to do with the fact that we live in a less populated part of the galaxy. Maybe we do, maybe we don't. Okay, so we've gone through one solar system, the star, our sun, and the planets around it. But we know that our star is not the only solar system. We know there are thousands of different systems out there. We know there are billions of stars. And now we just want to think here, when you look at the night sky, how many stars do you think you see? And there are a lot, right? There are a lot of stars that you can see in the night sky. And before we get into numbers here, I just want to do another fun fact that I really like. You all know the song, Twinkle, Twinkle, Little Star. Have you ever asked why stars twinkle and planets don't? We can see Venus in the night sky pretty frequently. We can see Mars. You can also see Jupiter, Saturn, but with the naked eye, just looking up in the night sky, you can frequently see these planets. And if you've ever been able to see these planets, they look solid. They look like solid objects, whereas all stars twinkle. So if you've ever wondered what causes stars to twinkle and planets to appear solid, I have the answer for you for that as well. And let me bring up another visualization by James. This is the same person who did the image before. Okay, unless you're in the middle of LA, then you only see 10 stars. Yeah, that's true with most cities. So let me just take myself away here. Now, the reason that stars twinkle has nothing to do with the star itself. It actually has to do with the way it emits light, or basically, not even the way it emits light, sorry, the way it appears in the sky. Now, stars are really, really, really far away, which means they basically what we call a point source. They only send us one beam of light in a straight line, and this is what we look at. Now, in our atmosphere, this photon, this particle of light, or this beam of light is going to get absorbed, re-emitted, it's going to get diverted. So you see this star comes in, it goes through the atmosphere, it moves around a lot. And what happens is when you're trying to look at the star, you see it moving. This leads to the twinkling effect. On the other hand, when we look at a planet, they're much closer. They're smaller, but they're a lot closer. They're so closer that they're no longer just one point in the sky, but rather they have a broad area. So they emit several beams of light that come to us. And even though each of these individual beams of light moves around, they move around a bit, but not enough to make the whole system twinkle. They look slightly blurry, especially around the edges. You still get this slight twinkling effect, but they look solid. So in answer to your question, David, this video, as I said, is produced by James O'Donoghue. It is not produced by me. And he shares them publicly on his Twitter, usually the low definition version on his Twitter account, and the high definition version on his YouTube account. The version I am showing you here is the low definition version taken from his Twitter account. If you want the high definition version, please go over to his YouTube channel and check it out there. So that's why large telescopes have adaptive optics, to remove the shimmering effect caused by our atmosphere. Exactly. So we really need to remove this shimmering effect. But if you've ever wondered why stars twinkle, it's actually because of our atmosphere. So I think this image is a great way of visualizing it. Again, if you like these type of images, do check out James on Twitter and his YouTube account, because he has amazing images like this. Okay, so I just wanted to just throw that fact in here, so why stars twinkle, because that's also something you might want to know. And today is about fun and crazy space facts, so we needed to throw in this fun and crazy space fact. Okay. Did I just remove myself from the screen? I've got so many things coming up here. I've got images on the screen share, and I just managed to remove myself from the screen. Okay, but we were going back to the idea of looking up at the night sky, hopefully not in a city, and you see thousands of stars up there. Now, let's just get the actual number. In the Milky Way, is it true the only stars we can see in Earth's sky with our eyes are just from our own galaxy? Absolutely. Now, when you look at the night sky, you can actually see other galaxies. I think there is one, if you're in super good visibility, there's one or two you can see with naked eye. With a telescope in a place with great visibility, you can pick up quite a few galaxies. But almost every star, so every single star you see in the night sky is from within our own galaxy. And we can only see a very, very, very small part of our own galaxy. But yeah, Andromeda, you can pick up if you have amazing visibility, really good night sky. Then you can see it. I picked it up with my telescope once or twice as well. You really do need a good sky for that, though. Okay, so let's get the actual number. How many stars are in the Milky Way? And there are actually 10 billion stars in the Milky Way. Now, I know we've had a lot of big numbers today, but big numbers are always hard to visualize. So let me just bring it up on screen here, this number here. So 10 billion not 10 billion, yes. Between 10 and 100 billion stars in the Milky Way, which is our galaxy. And this means that it's a 1 followed by 11 zeros. And this is, 11 zeros if we're counting 100 billion stars. Sorry, I should say 100 billion stars. 100 billion stars you should see now appearing up here on your screen. We'll take a second. Here it is. This is the amount of stars in the Milky Way. It's 100 billion. It's between 100 and 400. I'm going to take the low estimate of 100 billion. Who counted them? Yeah, right. You can try to count them, you won't get far. What we do is we count the ones in our patch, we kind of count the ones that we can see, we take the estimate of our size of the galaxy, and you get this 1 followed by 11 zeros, 100 billion stars. Absolutely ridiculous amount of stars. So David is just saying we can see Andromeda Galaxy, yep, as well as LMC and SMC, the Large Magellanic Cloud and the Small Magellanic Cloud. I have actually not seen those myself. 100 billion stars in the Milky Way. Ridiculous. Oh, thanks for joining us. It was great to see you. Thank you for being here. Basically, the same estimation process that we do to approximate the number of neurons in the brain. Yeah, you can't really count all of the neurons in the brain. You just count them in a small region and say, I assume this is statistically significant. This is the size of my brain. You multiply it. That's how you get the number. Okay. 100 billion stars in the Milky Way. And the Milky Way is just one galaxy that we know of. Okay, how many galaxies are there in the universe? A lot. Let me just show up an image here of the Hubble Space Telescope. This is known as the Extreme Deep Field Image. This was taken by Hubble, one of the most profitable telescope missions we've ever launched. You've probably all seen amazing images by Hubble here. Every dot, every glowing object you see here is not a star, it's a galaxy. This image contains over 5,000 galaxies. This is an image from the Hubble Space Telescope, composite image. The extreme deep field, I believe this is 21 days of exposure time, ridiculous. 5,500 galaxies in this image. It's absolutely mind-blowing. I'm almost out of water. Oh, we've been going for an hour and a half. About 10 more minutes, I think. 10 more minutes, we should get through a lot of them. Okay. 100 billion stars in our galaxy, and our current best estimates is that there are about 200 billion galaxies in the known universe. So let me just push that number to the program again. You should see it. I can't point to it directly. Top right, top left of your screen, sorry. 2 followed by 11 zeros. That's 200 billion galaxies that we believe of in the universe. Had no idea that's how long the exposure was. Yeah, I think it was 21 days. It's ridiculous. So if you believe aliens don't exist, then it's an awful waste of space. Yeah, so we've just gone through the idea that our galaxy has 100 billion stars. We know of about 200 billion galaxies, which means there are about 2 times 10 to the 22. I'm not even going to try to do that in billions and trillions and so on. 2 times 10 to the 22, that's 2 followed by 22 zeros. That's how many stars there are likely to be in the universe. And again, this is a ridiculously big number. So let me just put it up on the screen again, if I can find it. Okay, just pushing this number to the screen, you'll see a number with a lot of zeros appearing up here. Should appear up here. I figured out which direction to point now. That is how many stars we estimate are in the universe. 2 times 10 to the 22. That's 2 followed by 22 zeros. It's a ridiculous amount. I'm just going to put it on the screen again in case you missed it, because I took the time to type this up beforehand, so now I get to push it to the program. You can see it again about to appear up here. That's how many stars we estimate are in the universe. And, you know, we found now that having planets is much more common than not having planets, which means a lot of these stars probably have 1, 2, multiple planets. Our star has 8. There's probably a lot more planets out there. And a lot of these planets have moons. So that comes back to Andy's comment there of how likely is it that we are the only system, the only planet in the entire universe that has life? Because, you know, we saw the solar system is ridiculously big, right? We are this tiny planet in this huge solar system. And our solar system is one star in a ridiculously big galaxy, which is one galaxy in a ridiculously big universe. You know, human beings are these tiny, tiny, tiny specks of carbon lost on this planet, adrift in the universe. And yet somehow we aren't here. We are studying the universe. We are asking these questions. We are having these conversations. Absolutely amazing. You know, I hope my plan so far is 2 things. On the one hand, convince you how small we are, and on the other hand, convince you of how ridiculously big the universe is, but that it's so cool that we're here. So I just mentioned potential planets in the potential planets. So let's 20 trillion billion. Thank you, David, for checking that number. 20 trillion billion. That's much easier than 10 to the 22. And I actually wanted to do that calculation myself, but didn't because I ran out of time. Okay, so far, I just mentioned about planets, and this was hypothetical, like just estimating we have this many stars, we have this many galaxies, we know how many planets are here. How many planets have we actually found outside of the solar system? Sorry, yes, outside of the solar system. Yes, exactly. How many planets, actual planets, we're not talking about stars now, actual planets. How many planets do you think we found? I'll let you guess this. David, you probably know the answer. Feel free to guess as well. How many planets do you think we found outside of the solar system? I'm gonna stop, take a drink, and let you all come up with your answers to how many planets have we found, actually been able to find outside of our solar system. Now, of course, you want to remember here that finding planets is very hard because planets don't have their own light. Planets will reflect light from a star, but they don't emit their own light, which means if you look at another star, you're not going to be able to see the planets around them because the star from the light coming from the star is so bright, and the planets are just reflecting a bit of light that you would not be able to see them. So I see David there guesses 4,000. Georgia, you guess 2,400. So the actual answer currently is about 4,600. And these are planets outside of our solar system. 4,600 planets that we have been able to find, even though we cannot directly see them. Most of the time, these are planets that we see we look at a star and we see that every 100 days it gets very slightly dimmer, which probably means there is a planet going around. Thank you for the link, David. I really appreciate you plugging in the links here. So we have been able to find 4,500 planets. And Georgia, your guess of 2,000, sorry, Gloria, I misread your name there. Gloria guessed 2,400. So, Gloria, 2,400, your number is actually in some regard correct, because there is one space telescope, which is the most profitable one in terms of discovering planets, which is Kepler. Kepler, the space telescope, was launched in 2009. Unfortunately, it was decommissioned in 2018 after 9 years of service, which was a lot more than we initially planned. Kepler by itself found about 2,400 planets. So if you'd heard the number 2,400 somewhere, it's because those are the ones that were found by Kepler. We have another about 2,000 found with other systems. But just the idea here of how do we find these planets, because we cannot directly see them. There's a comment here by Andy that someone's slacking because there are probably millions. Absolutely. There are probably billions and billions of planets out there, but they're so hard to see because they're hiding. You know, they're dark compared to the stars and all of the bright objects. They're just these chunks of rock or chunks of gas even, just like gas giants that just reflect a bit of light. So what we try to do is we look at if a star moves very, very slightly because of a planet, or if the light diminishes slightly because of a planet. 4,500 to date. But all of these are within a tiny, tiny, tiny patch of the solar system. And let me just show you how tiny patch of the solar system. So this is an image made by NASA. Let me just take myself out of view here. This is obviously our best guess of what the Milky Way looks like, because we haven't been able to leave the Milky Way to take a picture. This is the Milky Way. You can see kind of down in the middle, there's this red circle. We are at the center of this red circle. The red circle is around the solar system. Now, I hope you can see the green triangle off to the left. The green triangle you can see heading off to the left is the place we've currently looked at for exoplanets. Just this tiny, tiny, tiny little corner of the Milky Way, the green area. And within this green area, we have found 4,500 planets within this tiny green area. The red area is, so the green area, is the area that's investigated by Kepler. The red area is the area investigated by another mission known as TESS, which is terrestrial, can't remember the acronym, the TESS telescope. So between TESS and Kepler, they've covered the red and the green area. And all of the 4,500 planets we found are in this small area. There is an upcoming mission planned known as the Nancy Grace telescope, the blue one. Sorry, the Nancy Grace Roman Space Telescope. You need to get that right, named after an amazing woman. And this is expected to look into the center of the Milky Way, and it's expected that it's going to find 100,000 planets. So I believe this will launch in a couple of years, and this is going to look in this whole blue triangle. 4,500 planets just in this tiny green and red area, and we've already found 4,500. With the upcoming Nancy Grace telescope, we're expected to find 100,000 more, which is just ridiculous numbers. Like, these numbers are seriously so ridiculous. I keep forgetting to put myself back on screen when I do this. So we have just looked at a tiny area of the solar system. Transiting Exoplanet Survey Satellite. Thank you, David. I am really bad with acronyms. And really, thank you for posting all of these links. If you want any more information on what I'm talking about, check out the links that David is really happily sharing here. Have all of these links. I realized I wanted to do a comparison before that Ian would probably like, when I was talking about these 200 trillion billion stars. That sounds like a huge number, right? We said there were 2 followed by 22 zeros. That's how many stars there are in the night sky. But just to go in the opposite direction of sizes, if you have a spoonful of water, just take a teaspoon of water, there are more atoms in this teaspoon of water than there are stars in the whole universe. So we think this number of like 100 trillion billion stars in the universe is ridiculously huge. But in a teaspoon of water, you have more atoms than there are stars in the entire universe. In every single human, there are about 1 million times more atoms in a human than there are stars in the entire universe. So this is just to give you some idea about numbers here, because we talk about these ridiculous numbers. You might have heard the comparison before that there are more stars in the night sky than grains of sand on the whole planet Earth. This is true. there are more trees on planet Earth than stars in the universe. That is also true. In fact, I did a whole broadcast about this, about different sizes and scales and going up and doing all these comparisons. And I'm just going to post a link here again. I actually found a link to some of my old broadcasts. This one was not specifically mentioned in the title, but this broadcast that I've just posted in the comments is one where we covered the whole size and scale of the universe for a whole hour. So what I'm doing now quickly, now is basically a summary of like 10 of my broadcasts. I blame Happs for this broadcast because they set up the Happs Space Challenge, and how could I not up my game for a Happs Space Challenge? I had to come with all the space facts, not all of them, but a lot of them. Okay, so we have the idea now. I hope I've convinced you that the universe is ridiculously big. The universe is huge and massive and full of empty space. We saw how much empty space there is in the solar system. Most of the universe is empty space. The universe is so big, we can't imagine it. It took us ages to scroll through the solar system. The solar system is one system, one star in one galaxy, which is one galaxy among billions of galaxies in the night sky. And the universe is big and old and crazy. And I say old, the universe is like 13.87 billion years old. Anybody who was with me last week knows, because we calculated this directly. We did the whole comparison with the latest data. Thank you for the comment there, David. So, thank you for the WOW award. So yeah, the universe is vast and big and ridiculous and 13.7 billion years old. And one cool thing is that we can still see light from the birth of the universe, or from the afterglow of the Big Bang. If you look around your night sky in any direction and you go to the microwave frequency, you can still see the afterglow of the Big Bang. Right? You can still see the earliest light in the universe produced. It's still around us. We can still use this to get images. We can still use this to know that the universe is 13.7 billion years old. I just want to give you another fact here that will hopefully help us, because I might have scared you. I've just been talking about how ridiculously big the universe is, and it is kind of scary to think about. The universe is 13.87 billion years old. It's bigger than we can conceivably imagine. We are just this tiny, tiny, insignificant species on this insignificant planet in an insignificant galaxy. And yet, we are an amazing species. Because you've probably all heard the famous quote from Carl Sagan that you are stardust, and this is true. But we're not just stardust. We are actually stardust and universe dust. Part of us was actually formed a few minutes after the Big Bang, which means 13.8 billion years ago. So all of the hydrogen and helium in the universe, all of the hydrogen that we know of in the universe, which is in every single star, was formed 3 minutes after the Big Bang, when the first atoms came together. This is when we first formed hydrogen. And humans have hydrogen in them. So let me just bring up this image now and put it in first place. The average human is composed of about oxygen. I can't see the numbers on my screen. Sorry, 65% oxygen, 18% carbon, 10% hydrogen, a bunch of nitrogen, and a few other things like calcium and phosphorus. But this means that 10% of us is hydrogen. And this 10% was formed at the time of the Big Bang, at the 3 minutes after the Big Bang. I actually have a really cool image here just to show this. So you can see on the screen now of where all of the elements come from. You can see in blue are the elements that come from the Big Bang. In green, you can see the ones that come from supernova. So all of the carbon in your body was formed in an exploding star. All of the oxygen in your body was formed in an exploding star. But 10% of you, the 10% of you that is made of hydrogen, was formed 13.8 billion years ago, 3 minutes after the Big Bang. Part of every one of us is really old. Yeah, we are all ancient. We are tiny, we are small, we are insignificant, but we carry the universe within us. Part of us is from the early universe. When you're done with your atoms, when you're no longer using them, those atoms will go back to the universe. That hydrogen will go on to become something else. Some of our atoms are 13 billion years old, and they will live on long past us. So, we are small, we are tiny, we are one of these insignificant species on an insignificant planet, and yet we carry the universe within us. And That is absolutely amazing. This is something that I find very comforting because, the universe is vast and scary and crazy. How certain is that 3-minute figure, and how do we know? Length of reaction time? Yes. So basically, what we do here is we consider as the universe gradually cooled down, what energy can you actually start to have protons come together to form these initial, so what energy did we form these protons, these initial chains in the early universe? And we can calculate the energy needed for this. We can calculate approximately, we know how energy has changed throughout the history of the universe. And about 3 minutes after the Big Bang, we're pretty sure on this, 3 minutes after the Big Bang is when these first actual atoms could begin to form. They didn't have electrons at that point. I just had a really weird noise outside my main door here. So we didn't have atoms at this point. We just had these initial protons. So we had these protons 3 minutes after the Big Bang. And so I imagine you can't hear that. There's just some strange noises. You can see I have my main door here, and there were just some strange noises. If anything happened, I'm on camera anyway. Okay, so yeah, we have these protons formed 3 minutes after the Big Bang. We're pretty sure of this figure because we can look around in the universe and see some really old regions of the universe where there's only hydrogen, and we can use it to get this number, these 3 minutes after the Big Bang. That's when the temperature drops too far below to fuse. Exactly, thank you, David. So that's the point where we can actually form these initial protons, and where you can no longer do other things with them. You're stuck with the hydrogen at that point. So even though we are tiny, we are insignificant, we are on this tiny, tiny, tiny planet, we are part of the universe, and the universe is part of us. And I think that is absolutely amazing. That is really, really, really cool. I'm just going to share another one of my broadcasts in the comments here, which is one of possibly my favorite broadcasts I've done here on Happs. It was just called 8 Fun Facts About the Universe. And in this broadcast, we looked at exactly that. We looked at 8 fun facts about the universe. It was super fun for me, at least. It was really cool broadcast to do. I had great fun. And one of the 8 fun facts we discussed in that broadcast was all of this about where your atoms come from and how you fit in the universe. Of course, that's also the broadcast where I told you all that the universe could end at any second without any warning. Without any warning, the universe could just end, wipe us all out, completely disappear, completely stop existing, and there will be no warning and absolutely nothing we can do about it. But we don't really need to worry about that too much because there's nothing we can do if it happens. The universe just decides to end, there's nothing we can do about it. That is known as vacuum decay, and that was, I believe, my opening fun fact for the 8 fun facts about the universe. So if you do want to know more about how the universe could just wipe us out, do check that out. If you don't want to do that, just say with a happy thought that we carry the universe in us, and we are part of the universe. Okay, 2 questions. What caused the Big Bang? And what caused the Big Bang? The Big Bang designed the 3 minutes. Okay, those are big questions that I'm not going to get into now because we're coming up to almost 2 hours of this broadcast, and it is almost 10 p.m. and those questions require their whole broadcast. So I'm usually online every weekend doing a general Ask Me Anything about the universe. I would ask you to come back with those questions another day and we can discuss them, because if I get into that now, we're going to be here all night. But it's a great question. I really hope you do come back and ask me on another broadcast. So I just want to finish on one comment here. The purpose of this broadcast, apart from just sharing some cool space facts because of the Happs Space Challenge, the purpose of this broadcast was to tell you that we're all small, we're all insignificant, the universe is ridiculously big. But despite how small we are compared to the universe, we are part of the universe, and part of our atoms come from this early universe. I think something that I find really comforting, and despite how scary the universe might be, we can actually understand the universe. We are probably the first generation, we are definitely the first generation of humans to ever know for sure the composition of the universe, the age of the universe, with percent level precision. I can tell you that everything you can see in the universe is only 4.9% of the universe. There is 95% of the universe, or 95.1% of the universe that we cannot see. This is 69% in the form of dark energy, the rest is dark matter. These are components that we cannot see. The universe is vast and crazy and ridiculous, but it is understandable. We know that there's 95% that we cannot see, and somehow we still know that it's there, and we can study this. My research is asking the question of how do we study what we cannot see in the universe. The cool thing is we can get these answers. Universe is crazy, it's scary, but it's also understandable. And the fact that it's understandable, or at least that we like to think that it's understandable, is something that I find really comforting. My broadcast here, I try to convince you that the universe is amazing, that we can study it, that we can actually get these answers. A question here of what caused the Big Bang, okay, that's maybe a bad example, but what was the Big Bang like? What happened? How long ago did it happen? What did this imply? These are questions we can actually answer. I get paid to answer these questions, which is absolutely amazing. So, okay, I hope I've convinced you that we are small, but we are significant. We are part of the universe, and we are here to study it, and we can ask these questions, and it is ridiculously cool. And I am coming up to 2 hours on what should have been a 1 hour broadcast. I knew we would go over time, and I drew up my list of like 19 facts. I think by now we've covered more than 19 facts. I think we've covered closer to 30. Thoroughly enjoying my presentation. Thank you so much, Gloria. I really appreciate your comments. Thank you. And thank you, Andrew. I really do appreciate your comments. I love broadcasting. I love talking about the universe. Thank you for that comment, Andy. I appreciate that. So I love sharing my passion about the universe with you all. Thank you for the great reporting award, David. I hope you'll come back to my future broadcast because I love doing this. Without your questions, I would just be here rambling by myself. So I love that you will come in and ask questions and have these discussions with me. Thank you, David, for the Super Heart Award. I really appreciate it. Okay, so this was an extra broadcast just because of the Happs Space Challenge. Thank you, Peter Pablo, for setting this up. I had to do the Happs Space Challenge. I hope this does count as a good entry for the Happs Space Challenge. Next weekend, I have a special broadcast planned. Instead of doing my usual Q&A of Ask Me Anything About the Universe, next week, I'm actually going to be joined by a friend and colleague in New Zealand, so we're changing the time of the broadcast slightly. And what we're going to try to do, thank you, Andy, for the Super Heart Award, and thank you, Sally, for your nice comments. What we're going to try to do next week is actually walk you all through a scientific paper, a current paper in cosmology. Because by now you've all asked me, my regulars at least, you've all asked me questions, you might have heard the same answers. The universe cosmology has a lot of ongoing research. We're not always just asking the same questions. So our plan next week is to try to walk you through one of the most recent, very interesting papers in cosmology that could have implications for our field, and it's something all of my colleagues are talking about. So next week, we're going to try this format of just walking you all through a scientific paper with the idea of showing you what type of questions we're asking and what type of questions you can ask. This is going to be a trial. If it works, we might do more of them. I will be joined by somebody who is thinking of getting into live streaming, so feel free to help me convince him to stay on Happs next week. The broadcast should be at Sunday, 8 p.m., so the same time as today, but on Sunday. Sorry, 9 p.m. my time. So I will announce it a few days in advance. It will be available on Happs. If you want to see my upcoming schedule, always check my Happs profile. I announce my broadcast at least 24 hours in advance. So I will schedule the broadcast for next week. I think it's going to be a good broadcast. It's going to be different to my usual ones, but it should be a fun challenge to do. So I hope you'll all join me next Sunday, a few hours later than usual. I will post the exact time. Whew, this was a long broadcast. I'm completely out of breath, completely exhausted. I am going to go crash in bed now. But thank you, everybody, for being here. This was super, super, super fun. I really enjoyed chatting to you all. Thank you all for the comments, for the awards, for the questions. It's been great to have you all here. I will be online again next Sunday. In the meantime, I hope you all stay safe, take care of each other, and go look out for all of the other Happs Space broadcasts, because there are going to be a lot of fun broadcasts this week. Good night, everybody.